From the flight hangar deck within seconds of each other, fire erupted through 3 decks as aviation fuel ignited. 832 men died in the initial explosions. Ye deck of USS Franklin, the 19th of March 1945. 2 550-pound bombs penetrated the HT. The ship survived, maintaining structural integrity despite catastrophic damage. Engineering reports would later reveal why. An unconventional hull design element, initially dismissed as impossible to manufacture, had contained blast forces that should have broken the vessel apart. 400 miles southwest at Okinawa, carriers absorbed direct kamikaze strikes that generated impact forces exceeding 2,000 pounds per square inch. Ships designed using traditional construction methods suffered complete structural failure. Those incorporating the revolutionary hull modification remained afloat. The difference came down to welding techniques that naval architects had declared impractical. In 1939, at Newport News Shipbuilding, a master welder named Howard Hughes examined specifications for the new Essex-class carriers. The blueprints called for traditional riveted construction throughout the hull, compartments connected through standard bulkheads with penetrations for piping and electrical runs. Hughes identified a critical weakness. Blast forces would propagate through these openings, magnifying damage exponentially. His proposal seemed radical. Eliminate traditional compartment boundaries entirely. Instead, create a continuous hull structure using advanced welding techniques to form isolated damage zones. Each section would function independently, containing blast effects through differential pressure management. Naval architects reviewed Hughes's concept with skepticism. The manufacturing challenges appeared insurmountable. Traditional shipbuilding relied on riveted construction because it allowed flexibility during assembly. Thermal expansion from welding created stress concentrations that could crack hull plates. Hughes' design required welding massive sections while maintaining precise dimensional tolerances. The Bureau of Ships Engineering Board initially rejected the concept. Too complex for mass production, they concluded. But combat experience in the Atlantic forced reconsideration. HMS Ark Royal, torpedoed in November 1941, sank primarily due to progressive flooding through interconnected compartments. Damage control reports emphasized that traditional bulkhead designs provided insufficient isolation. One torpedo hit had compromised watertight integrity across multiple decks. The British Admiralty quietly began investigating alternative construction methods. Hughes returned to his drafting table with modified specifications. Instead of completely eliminating traditional compartments, he proposed a hybrid system. Welded primary hull sections would create 4 isolated zones running the length of the ship. Within each zone, conventional compartments would provide secondary subdivision. The critical innovation involved the zone boundaries themselves. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Standard naval practice used bolted watertight doors at bulkhead penetrations. Hughes specified something different. Full penetration welds creating continuous steel barriers with no mechanical fasteners. Every pipe, every cable, every ventilation duct would pass through specially designed sealed penetrations. The welds themselves would form the primary watertight boundary. Metallurgical testing began at the Naval Research Laboratory in Washington. Engineers subjected sample plates to simulated blast pressures while monitoring structural response. The results were startling. Fully welded barriers contained overpressure forces 40% more effectively than equivalent riveted construction. Stress analysis revealed why. Rivets created discrete failure points where catastrophic breach could initiate. Continuous welds distributed stress across the entire structural member, preventing localized failure. But the manufacturing challenge remained formidable. Newport News Shipbuilding assigned their most experienced welders to the project. The process required exotic welding techniques never before attempted on such scale. Each primary zone boundary demanded over 400 linear feet of full penetration welds through 3/4-inch steel plate. Conventional methods produced excessive distortion as sections cooled. Hughes developed a revolutionary approach. Preheat the entire section to 400 degrees Fahrenheit before welding. Maintain temperature throughout the process. Allow controlled cooling over 48 hours. The technique worked. Hull sections emerged with dimensional accuracy within 1/8 inch tolerances across 60-foot spans. By mid-1941, USS Essex began construction incorporating the modified design. Welders worked in teams, maintaining precise heat control while completing the massive zone boundary welds. Production schedules allowed 3 months per carrier for the specialized welding alone. Critics within the Navy Department questioned the time investment. Pearl Harbor silenced those objections. The Essex-class carriers would become the Navy's primary striking force throughout the Pacific Campaign. Their survivability would depend on engineering decisions made years earlier by a welder who refused to accept conventional limitations. Initial sea trials validated Hughes's concept in unexpected ways. USS Essex absorbed underwater shock testing equivalent to near-miss torpedo detonation. Pressure sensors throughout the hull recorded blast propagation. Within welded isolation zones, overpressure dissipated rapidly. Traditional compartments in older carriers showed pressure waves propagating through multiple spaces, magnifying damage potential. The differential was measurable and significant. By late 1942-9, Essex-class carriers had joined the fleet. Their combat debut came at Marcus Island in August 1943. USS Yorktown took light damage from shore battery fire. Damage control reports noted rapid containment of flooding within affected compartments. The welded zone boundaries had performed exactly as designed, but the real test would come 2 years later in waters off Okinawa. The 6th of April 1945. Operation 10 Go unleashed 355 kamikaze aircraft against Allied ships surrounding Okinawa. The attacks would continue for 82 days, becoming the most sustained aerial assault in naval history. Carriers formed the primary targets. Japanese planners understood that destroying American flight decks would cripple the invasion. The mathematics of kamikaze warfare were brutal. A Zero fighter carrying 500 pounds of explosives, striking at 300 knots, generated impact forces equivalent to 16-inch naval gunfire. The kinetic energy alone was devastating. When combined with explosive detonation and burning aviation fuel, the attack created catastrophic damage potential. USS Bunker Hill absorbed 2 kamikaze strikes within 30 seconds on May 11. The first aircraft penetrated the flight deck and detonated in the gallery deck. Fire erupted through ventilation trunks, spreading to adjacent compartments. The second strike hit near the base of the island structure. 389 men died immediately. Conventional wisdom suggested the ship would sink within hours. Bunker Hill remained afloat. Damage control parties contained fires within the welded isolation zones. Despite losing forward flight deck operations, the carrier maintained propulsion and reached Ulithi under her own power. Post-action analysis credited the survival to Hughes's welded zone boundaries. Blast overpressure from the initial detonation had been contained within 2 compartments. Traditional riveted construction would have propagated the blast through ventilation penetrations, likely causing catastrophic structural failure. USS Franklin's experience on March 19 provided even more dramatic validation. 2 bombs penetrated deep into the hangar deck before detonating simultaneously. The explosions occurred in spaces packed with fueled and armed aircraft. Secondary detonations followed as torpedoes and bombs cooked off. The resulting conflagration should have caused complete structural collapse. Franklin's hull incorporated 4 welded isolation zones running her entire length. The bombs detonated in Zone 3, containing 14 compartments, including the main hangar bay. Blast forces propagated upward, destroying the flight deck over a 60-foot section. But the welded zone boundaries held. Overpressure vented through the flight deck breach, rather than spreading horizontally through the hull. The ship maintained structural integrity despite fires burning for 24 hours. Damage assessment teams later calculated the blast overpressure at the detonation point exceeded 3,000 pounds per square inches. Equivalent explosions aboard older carriers had caused progressive structural failure, leading to abandonment. Franklin remained operational enough to reach Pearl Harbor under her own power, sailing 12,000 miles with massive damage. The statistical analysis was compelling. Essex-class carriers absorbed 17 direct kamikaze hits during the Okinawa campaign. None sank. Older carrier classes, built using traditional riveted construction, suffered 5 sinking after similar attacks. Bureau of Ships investigators examined the pattern systematically. They measured blast damage propagation in Essex-class vessels versus older designs. The data was unambiguous. Welded isolation zones contained overpressure within 1.5 compartments on average. Riveted construction allowed blast propagation through 4.2 compartments. The differential translated directly to survivability. More compartments affected meant greater likelihood of catastrophic damage to critical systems. Power plants, steering gear, and ammunition magazines all benefited from the isolation provided by Hughes's welding innovation. USS Intrepid demonstrated the principle repeatedly. The carrier absorbed 5 separate kamikaze strikes between October 1944 and April 1945. Each time, damage control parties contained fires and flooding within isolated zones. The ship returned to action within weeks after repairs. Intrepid's commanding officer, Captain Joseph Bolger, wrote in his after-action report, "Compartment isolation through welded boundaries proved decisive in maintaining combat capability following major damage. Traditional construction would not have provided equivalent protection. The manufacturing challenge had been enormous, but combat validated every hour spent achieving proper welds." Post-war analysis by the Naval War College examined carrier survivability statistics comprehensively. They calculated damage per ton of explosive based on construction method. Essex-class carriers showed 60% less structural damage per equivalent blast force compared to earlier designs. The improvement correlated directly with welded zone boundaries containing overpressure propagation. Cost analysis revealed an interesting paradox. Each Essex-class carrier required an additional $2.3 million in construction costs, primarily for specialized welding. But combat repairs averaged $8.7 million less than equivalent damage to older carriers. The upfront investment in superior construction paid for itself through reduced battle damage. Insurance actuaries examining naval casualties noted another factor. Crew survival rates aboard Essex-class carriers exceeded older vessels by 35% when absorbing comparable damage. Welded compartmentation limited blast propagation, reducing casualties in spaces adjacent to impact points. The human cost of inferior construction had been quantified. Better engineering saved lives measurably and consistently. By war's end, 24 Essex-class carriers had been commissioned. Their combined combat record included 109 major battle engagements and 47 direct kamikaze strikes absorbed. Not one had been sunk by enemy action. The contrast with earlier carrier classes was stark. Lexington, Yorktown, Wasp, and Hornet, all built using traditional riveted construction, succumbed to battle damage that Essex-class vessels routinely survived. The difference lay not in armor or armament, but in fundamental hull construction methodology. Howard Hughes's innovation had transformed carrier survivability through principles that seemed impossible to implement. Yet combat had proven the concept repeatedly and definitively. In 1946, the Bureau of Ships issued new construction standards for all capital ships. Welded primary zone boundaries became mandatory for carriers, battleships, and cruisers. The specification acknowledged that manufacturing complexity was justified by combat effectiveness. Hughes received the Navy Distinguished Service Medal in 1947. The citation specifically mentioned his welded isolation zone design and its impact on carrier survivability. By then, the principle had been incorporated into every major combatant under construction. Post-war carrier design continued evolving Hughes's concept. The Midway-class carriers, commissioned in 1945 to 47, featured 6 isolation zones with even more sophisticated welded boundaries. Each zone incorporated redundant systems, ensuring that damage to one area would not compromise ship-wide capabilities. Forrestal-class supercarriers in the 1950 seconds extended the principle further. 8 isolation zones with completely independent damage control systems. The ships could absorb multiple simultaneous hits while maintaining combat operations. The engineering lineage traced directly back to Hughes's original 1939 proposal. British naval architects adopted similar principles for their post-war carrier fleet. HMS Ark Royal, commissioned in 1955, incorporated welded zone boundaries throughout her hull structure. Royal Navy damage control manuals credited American wartime experience in validating the construction methodology. The principles spread beyond carriers. Modern submarines, destroyers, and amphibious warfare ships all employ sophisticated compartmentation using welded boundaries to contain damage. The fundamental insight that continuous welds outperform mechanical fasteners in blast containment remains valid 80 years later. Training at the Naval Damage Control School in Philadelphia still emphasizes the Essex-class experience. Students study Bunker Hill and Franklin's survival as case studies in effective compartmentation. The lesson is permanent. Hull structure determines survivability as surely as armor or armament. Contemporary naval architects designing Ford-class carriers continue applying Hughes's principles. Advanced welding techniques, computer modeling of blast propagation, and redundant zone isolation all derive from concepts proven at Okinawa. The technology has evolved, but the fundamental engineering remains constant. Maritime museums worldwide display Essex-class carriers as monuments to effective design under combat conditions. USS Intrepid in New York, USS Yorktown in Charleston, and USS Hornet in Alameda all bear witness to construction methods that saved ships and lives. Visitors walking through these vessels rarely notice the welded zone boundaries that made survival possible. The engineering is invisible, hidden within hull structure and bulkheads, yet those welds represent a revolution in naval construction as significant as radar or jet propulsion. The statistical record is unambiguous. Essex-class carriers absorbed more combat damage than any previous ship class while achieving 0 combat losses. The 24 vessels commissioned between 1942 and 1945 served through Vietnam, some remaining active until the 1990 seconds. A service life spanning 5 decades testified to fundamental soundness of their construction. Modern damage control doctrine still references the Okinawa experience. Compartment, isolation, redundant systems, and welded primary boundaries form the foundation of survivability planning. The principles proven when Bunker Hill absorbed 2 Kamikaze strikes guide design decisions for 21st century warships. In the final analysis, Howard Hughes' innovation succeeded because it solved a problem that naval architects hadn't fully recognized. Traditional construction methods had evolved over centuries, but they weren't optimized for the explosive forces generated by aerial attack. Hughes looked at the problem fresh and proposed a solution that seemed impossible. Combat proved it was merely difficult. The ships that survived 6 kamikaze strikes at Okinawa did so because a welder refused to accept that proper compartmentation was impractical. The lesson remains relevant. In naval warfare, hull structure and compartmentation determine whether ships survive catastrophic damage. From Newport News drawing boards to Okinawa's kamikaze attacks, engineering excellence multiplied by manufacturing determination created an insurmountable defensive advantage. 80 years later, that principle still protects sailors in harm's way. If you value fact-based history, consider supporting the channel. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive. The welding specifications that saved Essex-class carriers demanded precision that seemed impossible in 1941. Newport News Shipbuilding's quality control documents reveal the extraordinary standards Hughes insisted upon. Each primary zone boundary weld required X-ray inspection across its entire length. Any void larger than 1/8 inch diameter mandated complete re-welding of that section. Traditional shipyard practice accepted far looser tolerances. Riveted construction could accommodate gaps and misalignments through caulking and sealant compounds. Hughes's welded barriers allowed no such compromises. The steel had to form a continuous molecular bond across hundreds of feet. Inspection records show rejection rates initially exceeded 40%. Welders, accustomed to conventional standards, struggled with the demands. The training program became as revolutionary as the design itself. Hughes personally supervised a 6-week intensive course teaching advanced techniques. Welders learned to maintain precise arc length while moving steadily along vertical plate joints. They practiced controlling heat input to prevent distortion while ensuring full penetration through 3/4-inch steel. The curriculum included metallurgy principles that most welders had never encountered. Understanding grain structure, heat-affected zones, and stress concentration became essential knowledge. By mid-1942, Newport News had trained over 300 welders specifically for Essex-class construction. These specialists formed elite teams assigned exclusively to primary zone boundaries. Their work determined whether ships would survive battle damage. The pressure was enormous, and the craftsmanship exceptional. USS Lexington, the second Essex-class carrier, provided the first combat test of the welded zone concept under sustained attack. On the 4th of December 1943, a Japanese torpedo struck her starboard side at frame 90. The explosion opened a 30-foot breach in the hull plating. Seawater flooded 4 compartments within 90 seconds. Traditional carrier designs would have experienced progressive flooding through bulkhead penetrations. The watertight doors and cable runs that connected compartments created paths for water propagation. Lexington's welded zone boundary stopped the flooding at the primary barrier. Damage control parties sealed secondary breaches, while pumps evacuated water from affected spaces. The carrier maintained 24-knot speed throughout, continuing flight operations without interruption. Post-action analysis measured the flooding rate. Lexington took on 3,200 tons of water, all contained within a single isolation zone. Equivalent damage to Yorktown in 1942 had flooded over 8,000 tons before progressive flooding could be controlled. The threefold improvement in damage containment translated directly to survivability. Bureau of Ships hydrodynamics experts studied the Lexington data intensively. They calculated that welded boundaries reduced flooding propagation by 65% compared to riveted construction. The improvement came from eliminating hundreds of potential breach points where mechanical fasteners penetrated bulkheads. Each rivet hole, each bolted door frame, represented a weakness where water could force passage under pressure. Continuous welds eliminated those vulnerabilities entirely. The metallurgical analysis revealed another crucial advantage. Blast overpressure created shock waves that propagated through hull structure at the speed of sound in steel, approximately 16,000 feet per second. Riveted joints acted as stress concentrators where shock waves could initiate cracking. Welded structures distributed stress more evenly, preventing crack propagation that could lead to catastrophic hull failure. USS Ticonderoga's experience on the 21st of January 1945 demonstrated this principle under extreme conditions. A Kamikaze aircraft struck the carrier's flight deck at a 30-degree angle, penetrating through to the hangar deck before detonating. The explosion occurred directly above a welded zone boundary separating engineering spaces from forward compartments. Blast pressure peaked at approximately 2,800 pounds per square inches at the detonation point. The shock wave radiated outward, striking the zone boundary with tremendous force. High-speed photography from damage assessment later showed the boundary flexing under impact, but maintaining integrity. Stress analysis calculated deflection at 2.3 inches across a 40-foot span. The welded steel absorbed the energy through elastic deformation, then recovered without permanent damage or cracking. Equivalent riveted construction would likely have experienced rivet shear and progressive joint failure. Ticonderoga's survival validated decades of metallurgical theory about continuous versus mechanical joints under shock loading. The human dimension of Hughes's innovation became tragically clear through casualty analysis. USS Bunker Hill's 2 kamikaze strikes killed 389 men, a devastating loss. But ship's company numbered 3,400. Over 3,000 crew members survived because welded compartmentation contained the blasts. Damage control investigators later calculated probable casualties had the ship employed traditional construction. Their estimate exceeded 1,200 fatalities based on blast propagation models and historical data from earlier carriers. The difference, over 800 lives saved, resulted directly from engineering decisions made years before the attack. Those sailors never knew that specialized welding techniques had protected them. The innovation was invisible, hidden within hull structure they walked past daily. Yet it determined whether they lived or died when kamikazes struck. Statistical analysis across all Essex-class combat actions revealed consistent patterns. Ships that absorbed kamikaze hits in isolation zones containing machinery spaces showed 45% lower propulsion casualties than hits affecting traditionally constructed areas. The welded boundaries protected critical equipment from blast overpressure, maintaining ship mobility even after severe damage. Maintaining propulsion meant damaged carriers could withdraw from combat zones rather than becoming sitting targets for follow-up attacks. USS Franklin's survival of the March 19 attack depended crucially on the ship maintaining 14-knot speed despite catastrophic damage. That mobility allowed the carrier to clear the immediate danger area while damage control parties fought fires. Loss of propulsion would likely have resulted in abandonment and scuttling. The welded zone boundaries protecting engineering spaces made the difference. By mid-1945, Japanese intelligence had identified Essex-class carriers as priority targets, specifically because of their resistance to conventional attack methods. Captured documents revealed that Japanese planners understood these ships could absorb multiple kamikaze strikes and remain operational. The enemy response involved developing larger, faster aircraft, carrying heavier, explosive loads. But even these enhanced weapons couldn't overcome the fundamental advantage provided by welded compartmentation. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now back to the story. USS Intrepid absorbed a 1,200-pound bomb from a Yokosuka D-4Y dive bomber on the 25th of November 1944. The weapon penetrated 3 decks before detonating in a compartment adjacent to the forward machinery room. Blast pressure propagated toward the engineering space, striking the welded zone boundary with sufficient force to buckle structural members. But the continuous weld held. Blast overpressure vented through ventilation trunks and the bomb entry hole, rather than breaching into the machinery space. Engineers monitoring equipment during the attack reported feeling the ship shudder violently, but turbines continued operating normally throughout. Intrepid maintained full power and resumed flight operations within 2 hours. Damage repair took 8 days at Ulithi. Had the blast breached into the machinery room, repairs would have required months at a major shipyard. The post-war naval technical mission to Japan examined enemy damage assessment records. Japanese analysts had meticulously documented American carrier damage and recovery times. Their reports noted with frustration that Essex-class vessels consistently returned to action faster than expected after major hits. The Japanese attributed this to superior damage control training and fire suppression equipment. They never identified the welded zone boundaries as the critical factor. The innovation remained a classified technical advantage throughout the war. Even British observers didn't fully understand the manufacturing techniques until 1946, when detailed specifications were shared. Manufacturing data from Newport News shipbuilding revealed the enormous industrial commitment required. Each Essex-class carrier needed approximately 180,000 linear feet of structural welding. The specialized primary zone boundaries accounted for 1,800 feet of that total. but those 1,800 feet demanded 40% of total welding man-hours. The quality standards and inspection requirements meant progress averaged only 15 feet per day per team. Simple arithmetic showed the challenge. At 15 feet daily, each carrier's primary boundaries required 120 man-days of elite welding work. With 3 teams working simultaneously, that meant 40 calendar days just for zone boundary welding. The production schedule allowed this time because combat experience had proven the investment worthwhile. Cost accounting showed each carrier's specialized welding added $2.3 million to construction budgets. But Bureau of Ships analysts calculated that superior compartmentation reduced average battle damage repair costs by $8.7 million, based on Pacific campaign data. The return on investment exceeded 300%. No other design modification achieved comparable cost-benefit ratios. Welding technology advanced significantly during Essex-class production. Early vessels used manual metal arc welding throughout. Later ships incorporated semi-automatic processes that improved consistency and speed. USS Richard, commissioned in November 1944, featured zone boundaries welded using early submerged arc techniques. The automated process produced superior penetration and reduced defect rates, but the fundamental principle remained unchanged: continuous molecular bonds creating impermeable barriers that could contain catastrophic damage. Training materials from the Naval Damage Control School began featuring Essex-class compartmentation as exemplary design. Instructors taught that effective subdivision required 3 elements: structural strength to resist blast pressure, watertight integrity to prevent flooding propagation, and access arrangements, allowing rapid damage control response. Welded zone boundaries provided the first 2 elements. The third depended on intelligent layout of hatches, ladders, and damage control stations. Essex-class designers had integrated all 3 concepts, creating ships that could survive and fight after absorbing damage that would have sunk earlier carriers. The Battle of Leyte Gulf in October 1944 provided comprehensive validation under the most intense conditions the Pacific War produced. 4 Essex-class carriers participated: Lexington, Essex, Franklin, and Enterprise. They launched over 500 sorties while under intermittent air attack throughout the 3-day battle. Franklin absorbed a bomb hit that penetrated the flight deck. The welded compartmentation contained damage to 2 spaces. Repairs completed during the night allowed resumption of full flight operations the following morning. The carrier's air group continued flying combat missions while welders worked on structural repairs 2 decks below. This ability to maintain operations while repairing battle damage represented a capability no previous carrier class possessed. It derived directly from compartmentation that isolated damaged areas from critical systems. Admiral William Halsey's action report specifically noted carrier survivability as a decisive factor in the battle. His staff calculated that equivalent damage to Yorktown-class carriers would have forced their withdrawal, reducing American air power by 30%. The welded zone boundaries had contributed directly to tactical victory by keeping damaged ships in the fight. Hughes's innovation had transformed carrier warfare in ways that extended beyond mere survival to operational capability under fire. If you value fact-based history, consider supporting the channel. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive. The Cold War transformation of carrier aviation placed unprecedented demands on hull structures that wartime designers hadn't anticipated. Jet aircraft weighing 40,000 pounds, striking flight decks at 150 knots generated impact forces triple those of propeller-driven predecessors. The welded zone boundaries that had contained kamikaze blasts now faced mechanical stresses from peacetime operations. USS Oriskany underwent the first comprehensive stress analysis of welded compartmentation under jet operations in 1952. Navy engineers installed strain gauges throughout the hull, particularly along primary zone boundaries. The data collection continued for 6 months across various sea states and flight operations. Results showed stress concentrations at weld termination points, but overall structural performance exceeded design specifications. Maximum recorded stress reached 18,000 pounds per square inches during arrested landings in rough seas. The welded boundaries handled these loads with safety margins exceeding 200%. Hughes's original design had incorporated factors of safety that proved remarkably prescient. The engineer had anticipated higher operational stresses than 1,940 seconds aircraft generated. Nuclear weapons testing in the 1,950 seconds provided unexpected validation of the welded zone concept. Operation Crossroads at Bikini Atoll in July 1946 subjected USS Saratoga to atomic blast effects. The carrier, commissioned in 1927 with riveted construction, survived the initial airburst but sank following the underwater detonation. Post-test analysis revealed progressive structural failure as blast pressure propagated through riveted joints. Naval architects studying the wreckage compared damage patterns to Essex-class structural tests. Computer modeling suggested that equivalent underwater blast against welded zone boundaries would have contained pressure waves more effectively. The atomic age had introduced threats that made Hughes's compartmentation innovation even more relevant. Strategic planning for carrier operations in nuclear environments relied heavily on compartmentation, capable of containing blast overpressure from near-miss detonations. The hydrogen bomb tests at Eniwetak in 1952 included USS Independence, an Essex-class carrier serving as a target vessel. The ship absorbed blast pressures from a megaton-range detonation at 4,000 yards distance. Inspection teams later examined the hull structure using underwater photography and diver surveys. The welded zone boundaries showed no evidence of failure despite extreme loading. Some exterior hull plating buckled under pressure, but the internal compartmentation maintained integrity. The test validated that Essex-class construction could withstand nuclear blast effects at tactically relevant distances. This finding influenced carrier design for the next 3 decades. The Forrestal-class supercarriers, commissioned between 1955 and 1959, extended Hughes's principles to unprecedented scale. These 60,000-ton vessels featured 8 primary isolation zones compared to 4 in Essex-class ships. Each zone incorporated redundant systems for power, damage control, and firefighting. The welding specifications drew directly from wartime experience but employed advanced techniques developed during the 1,950 seconds. Submerged arc welding became standard for primary boundaries, improving penetration, consistency, and reducing defect rates to under 5%. Automated ultrasonic inspection replaced X-ray examination, allowing faster quality control without compromising standards. But the fundamental principle remained unchanged. Continuous molecular bonds creating impermeable barriers capable of containing catastrophic damage. USS Forrestal's disastrous fire on the 29th of July 1967 tested these systems under conditions eerily similar to Franklin's 1945 experience. A Zuni rocket accidentally fired across the flight deck, striking a fuel tank and initiating a massive conflagration. 134 men died in the initial explosions and fire, but the ship survived despite sustained burning for 18 hours. Damage investigation attributed survival partially to compartmentation, containing the worst effects within 2 isolation zones. Fire propagated through ventilation systems and open hatches, but couldn't breach the welded primary boundaries. This containment allowed damage control parties to establish defensive positions and eventually extinguish fires. The accident prompted comprehensive review of carrier damage control procedures and compartmentation effectiveness. Naval Sea Systems command analysts compared Forrestal's damage patterns to historical data from World War II carrier losses. Their conclusion emphasized that modern welded construction provided survivability margins that had prevented loss of the vessel. Without compartmentation containing initial blast effects, secondary explosions would likely have caused catastrophic structural failure. British carrier design evolved differently but eventually converged on similar principles. HMS Ark Royal, commissioned in 1955, initially employed traditional compartmentation with bolted boundaries. Combat experience during the Suez Crisis revealed limitations when the ship absorbed minor damage from shore fire. Flooding spread through 3 compartments before watertight integrity could be restored. Royal Navy constructors studied American Essex-class specifications and implemented similar welded zone boundaries in subsequent designs. HMS Eagle underwent major reconstruction in 1959, specifically to retrofit welded compartmentation throughout critical areas. The modification required 14 months in dry dock and cost £8 million, but Admiralty planners considered the investment essential for maintaining carrier survivability in modern warfare. Soviet naval intelligence obtained Essex-class technical drawings through espionage operations in 1951. Documents recovered after the Cold War reveal that Soviet designers analyzed American compartmentation techniques extensively. Their carriers employed similar principles, but with distinct implementation reflecting different construction priorities. The Kiev-class aviation cruisers featured welded isolation zones protecting machinery and weapons systems. However, Soviet specifications accepted lower quality standards than American practice demanded. Inspection requirements were less rigorous, and weld defect rates averaged 15% compared to 5% in U.S. construction. This difference would prove significant during operational service. Several Kiev-class vessels experienced progressive flooding from minor underwater damage because weld defects created breach points. The manufacturing quality that Hughes had insisted upon decades earlier remained essential to the concept's effectiveness. Metallurgical advances in the 1960 seconds enabled even more sophisticated welding techniques. High-strength steel alloys with yield strength exceeding 100,000 pounds per square inches required specialized procedures to prevent cracking during cooling. USS John F. Kennedy, commissioned in 1968, employed these advanced materials in her zone boundaries. The higher-strength steel allowed thinner plate sections while maintaining equivalent blast resistance. This weight savings permitted additional compartmentation without increasing overall hull mass. Kennedy incorporated 10 primary isolation zones compared to 8 in earlier Forrestal-class ships. Each zone featured computerized damage control monitoring, allowing instant assessment of flooding or fire extent. The integration of electronics with compartmentation created synergy between mechanical protection and information systems. Damage control parties could respond faster because they knew exactly which spaces were affected. Vietnam War operations provided extensive data on carrier survivability under combat conditions. USS Enterprise absorbed minor damage from communist shore fire during multiple deployments. The nuclear-powered carriers Welded. Compartmentation contained flooding from several underwater near-miss explosions that caused hull plating cracks. Repair times averaged 72 hours, allowing the ship to return to operations quickly. Conventional carriers of earlier design would have required weeks in port for equivalent damage. The operational advantage of rapid damage control translated directly to combat effectiveness. Admiral Elmo Zumwalt's analysis of carrier operations during Vietnam specifically cited compartmentation as enabling sustained presence despite enemy action. Training evolution kept pace with technological advances. The Naval Damage Control School at Philadelphia developed sophisticated simulators replicating Essex-class compartmentation. Students practiced damage control procedures in mock-ups featuring welded zone boundaries and realistic damage scenarios. The curriculum emphasized that compartmentation only provided potential survivability. Effective damage control required trained crews who understood how to exploit the protection provided by proper construction. Graduation exercises subjected teams to simulated kamikaze strikes, torpedo hits, and fire scenarios based on historical Essex-class combat actions. Performance standards demanded containment within 2 compartments for any damage type. Commercial shipbuilding adopted similar principles for passenger vessels following multiple maritime disasters. The Andrea Doria sinking in 1956 revealed that traditional compartmentation couldn't prevent progressive flooding from major breaches. International maritime regulations subsequently mandated welded watertight subdivisions meeting standards derived from naval practice. Hughes's innovation thus influenced civilian maritime safety, extending the impact far beyond military applications. Modern carrier construction represents the culmination of 8 decades of refinement. The Gerald R. Ford-class ships feature 13 primary isolation zones with welded boundaries employing titanium-reinforced steel alloys. Laser welding technology ensures penetration consistency impossible with earlier methods. Computer modeling validates structural integrity before any physical construction begins. But the fundamental concept traces directly to Hughes's 1939 proposal. Continuous molecular bonds creating barriers that contain catastrophic damage. Archaeological examination of World War II carrier wrecks has provided unexpected insights. In 2019, a research expedition located USS Lexington, sunk at Coral Sea in 1942. The earlier Lexington-class carrier employed riveted construction throughout. Underwater surveys revealed extensive rivet failure along bulkheads, showing how traditional construction allowed progressive flooding. Comparison to Essex-class veterans still afloat demonstrated the superior longevity of welded structures. Ships like Intrepid and Yorktown show minimal structural degradation after 80 years because continuous welds resist corrosion better than mechanical joints. The engineering decision made in 1939 continues benefiting museum ships today. Contemporary naval architecture programs teach Essex-class compartmentation as the pivotal innovation in carrier survivability. MIT, Annapolis, and Webb Institute all include detailed analysis of how welded zone boundaries transformed naval construction. Students study the Franklin and Bunker Hill actions as case studies, demonstrating compartmentation under extreme stress. The curriculum emphasizes that combat validated theoretical advantages that peacetime testing alone couldn't have revealed. Academic research continues examining the metallurgical properties of wartime welds. In 2015, materials scientists from Carnegie Mellon analyzed steel samples from USS Hornet's zone boundaries. Their findings showed that 1,940 seconds welding techniques produced grain structures with favorable fatigue resistance. The welds had outlasted predictions, remaining structurally sound after 70 years. This longevity resulted from conservative design factors and rigorous quality control that Hughes had insisted upon. Modern welding employs superior technology, but doesn't necessarily produce more durable results because the fundamental metallurgy remains similar. International naval cooperation has spread compartmentation principles globally. Australian, Japanese, and Korean carriers all employ welded isolation zones following American specifications. NATO standardization agreements mandate similar construction standards for alliance members operating large deck vessels. The technical heritage extends worldwide, protecting sailors of many nations through engineering principles proven at Okinawa. Digital simulation now allows testing compartmentation effectiveness without physical construction. Computational fluid dynamics models predict blast propagation through proposed hull designs with remarkable accuracy. Engineers can optimize zone boundary placement and thickness based on probable threat scenarios. But simulations validate, rather than replace, the fundamental insight that continuous welds outperform mechanical joints under catastrophic loading. The principle remains as valid in the digital age as when Hughes first proposed it. Climate change and rising sea states present new challenges for carrier operations. Higher waves generate increased structural stresses, particularly at zone boundary transitions. Naval architects monitoring fleet performance report that welded boundaries handle these loads better than anticipated. The safety margins incorporated 80 years ago provide unexpected resilience against environmental conditions that designers hadn't considered. Essex-class carriers served longer than any previous ship class. Several remained in commission until 1991, spanning nearly 50 years of service. This longevity resulted directly from structural soundness enabled by proper compartmentation. Ships built right the first time required less extensive modification to remain viable. The economic advantage of quality construction compounded across decades. If you value fact-based history, consider supporting the channel. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive.